Okay, I'll get started. So just a word about the practice test that it's meant to be practice in the style, the format of the test. So it's got the multiple choice, it's got the numerical answer questions, and it's got the fully worked out problem. And that's the same style format as the real test. It's meant to cover the same overall material as the real test, i.e. covering chapters 1 through 4 like the real test, but you're not going to see the problems from the practice test on the real test. It'll be different problems that appear on the real test. Anyway, I'll start working through these, and yeah, please interrupt me or please stop me when things don't make sense. So the first question, I think I'm just going to read out the questions, and then I'll just solve them on the whiteboard. And so I won't try and write them down on the whiteboard. That would take me way too long because it's so painful for me to write on the whiteboard. But I will write out some sort of solution on the whiteboard. So first question is, kinetic energy is mass times the square of velocity divided by 2. So K equals 1/2 mv squared. And we haven't met kinetic energy yet. But the question is to find the dimensions of kinetic energy. And we're using dimensional analysis for this. So we're going to apply dimensional analysis and uncover the dimensions of kinetic energy from, which is on the left-hand side, K, from the dimensions of the quantities on the right-hand side, which are mass and velocity. And so to do this, all I would do, I want the dimensions of kinetic energy. I'm going to start filling in the dimensions of these quantities on the right. Well, the first one is 1/2. That's just a number. That has no dimensions. So let me at least make that clear by just writing no dimensions for the 1/2. The second quantity is mass. So that is a fundamental dimension in nature. So that's dimensions is just denoted m here. And then lastly, we've got velocity. And so the velocity, as you know, think about the definition of velocity, it's got dimensions of length over time. I could write it like this. And in the equation, the velocity is squared. And so all I have to do to figure out the dimensions of kinetic energy from dimensional analysis is combine or multiply through all these dimensions here. So we're going to get a mass in the numerator. We're going to get a length squared dimensions in the numerator. And we've got a 1/time here. So we're going to get a 1/time squared, a time squared in the denominator. And so that's the dimensions of kinetic energy. And that's just a topic that we discussed in I think the very first class. Question number 2. It says a ball is thrown vertically upwards. So just imagine throwing a ball vertically upwards. And we're told that the downwards direction is the positive direction. So this is a choice you can make often in solving problems. Supposing you're throwing balls or dropping balls, you can choose upwards to be positive or downwards to be positive. In this question, we're told we're choosing downwards to be positive. And then the question asks, what is the sign of the acceleration for the ball on the way up and on the way down? So we've chosen downwards to be positive. This is the positive y direction. Say. Now the ball itself goes up into the air and comes back down again. So that's the path of the ball. And if you think about the velocity of the ball, well, the velocity of the ball is upwards initially until it reaches the maximum height. So that would be in the negative direction. And then on the way down, the ball is, as it heads down, is in the positive direction. So velocity changes direction. And with this convention for the positive direction, it's negative on the way up and positive on the way down. Acceleration, on the other hand, the acceleration of gravity, that's downwards on the way up. So downwards is positive, and it's downwards on the way down. So that's also positive on the way down. And so that's the answer to this question, that the acceleration with this convention for the positive direction is positive on the way up and positive on the way down. And if you look here on the way up, because the acceleration is opposite the direction of motion, it's slowing the object down and bringing it momentarily to the rest. Then on the way down, because it's in the same direction as the direction of motion, it's speeding the object up, making it get faster. And so this is the answer to question number 2. Okay, I see, besides the, I just looked at the chat, beside the practice exam, how else should we be studying? Like, should we redo homework problems or read over the notes? Actually, that's a good question. So, as I say, the style of the practice exam is meant to be that it involves kind of the conceptual questions that we've done, multiple choice in lecture. It involves the style of homework problems that we've done, and also the fully worked out problem that you've submitted. So the more of those types of things that you could practice, the better. So there's lots more homework problems in the textbook than I've set as homework. And they're generally all very good practice for preparing for the test. So you could solve new homework problems that you've not previously met by just solving other homework problems from the textbook. You can go back through the old homework problems. The only, which is not bad, to go back to the old homework problems and check you can redo them. But I would say that because you're meeting them the second time, you're not getting that same experience as when you meet a problem for the first time. And on the test, you're going to get that experience where you meet a problem for the first time. And so doing new homework problems, in that sense, is better than redoing old homework problems. There's a question, is the practice exam graded? No, the practice exam is not graded. It's placed in a assignments folder that is practice assignments, and practice assignments folder has 0% towards your grade. Okay, so I'll go on to number 3 now. So this is a question that relates to mass and weight and the difference between mass and weight. And of course, in everyday language, we often use mass and weight to mean the same thing. And I mean, everyday language, I might use mass and weight to be the same thing. But in physics, we are careful that they're quite different. So mass is a measure of the quantity of matter. And elephants have lots of matter, mice have a small amount of matter. Weight is a measure of a particular force of gravity. And so, the weight of an elephant on Earth is larger than the weight of a mouse on Earth, because the elephant has more mass, the mouse has less mass. But the weight also reflects the acceleration of gravity on Earth. So the equation that I sort of think of as I was solving this problem is that weight is equal to the force of gravity, i.e. it's equal to, on the surface of the Earth, mass times the acceleration of gravity. And when I write this down, bear in mind that the mass here, that's a scalar quantity. It has no direction. Weight, force of gravity, acceleration of gravity, all have directions to them. So there's a difference there too. Anyway, getting back to the question, which I've now forgot. Compare your mass and weight on the Earth and the Moon. So your mass on the Earth and the Moon would be the same. Whether you're on the Moon or on the Earth, presumably you're the same amount of matter, the same amount of materials, so you're the same mass. Your weight will be different. The acceleration of gravity on the Moon is 6 times smaller than the acceleration of gravity on Earth. It's about 1.6 meters per second squared rather than 9.8 meters per second squared. And so, although your mass is the same, when you multiply by the acceleration of gravity, your weight will be different. It'll be smaller by a factor of 6 on the Moon or larger by a factor of 6 on Earth. Okay, next one. As I say, stop me if something's, unclear. Otherwise, I kind of think am I talking to myself and just reassuring myself that I know these things or not? Number 4. Number 4 says, imagine an arrangement of a frictionless pulley with 2 masses, M1 and M2, that are connected by a cable or a string or a wire or whatever. We're told that the mass M1 is bigger than the mass M2, and we're asked to compare the sizes of the tensions and the accelerations. So the tension forces experienced by the masses and the accelerations of the masses. So let me just draw this problem quickly. I hope that's not the virus. Anyway, so here's the picture. And remember, in this picture, M1 over here on the left is bigger than M2 over here on the right. And so we know that the heavier mass will fall and the lighter mass will rise. We knew that before we came in this class. So the question asks about tension and acceleration. So there's a tension over here on the left in the string here. And there's a tension over here on the right in the string here. But the key thing about this arrangement is this is one string that is connecting the 2 masses, joining the 2 masses. And that one string just transmits the tension force from one mass to the other mass, from one object to the other mass. So when you have 2 masses on a pulley like this, the 2 tensions, so there's a tension, running out of room to write this, but there's a tension T1 over here. And there's a tension T2 over here. Those are equal tensions because it's a single string. And so that's a key feature about such a problem with a pulley. In trying to understand the problem with the pulley, you have to recognize, you have to start with the fact that the tensions are the same. Also, the acceleration over here on the left and over here on the right, because the masses are attached by a string, although one acceleration's up and the other one's down, the sizes of the acceleration are the same. So the sizes of the tensions are the same and the sizes of the accelerations are the same for the 2 masses on a pulley. That's a key feature. These are the 2 key features in understanding the pulley system. And so the way to understand that is because it's really because it's a single string that's transmitting the tension, and it's a single string to which the 2 masses are attached. And so the tension is the same tension that's transmitted through the string. And also the separation of the masses is the same separation, the length of the string. So I hope that helps. These two facts then allow you to go on and calculate, for example, the accelerations and the tensions. Without these two facts, we couldn't calculate the tensions and the accelerations. Number 5. Okay, so number 5 says we've got a crate of mass m. It's attached to the cab of a truck by a cable, and the truck is accelerating with some acceleration a. And we got to figure the tension in the string. Let me just draw a little picture of this to the extent that I can. Okay, so here's the truck. Here's the cab of the truck. And then on the bed of the truck is a crate. Its mass is m. And it's attached to the cab by a cable. So that's one thing about the attachment of the mass to the truck. The other thing is that there's no friction on the bed of this truck. So it really only communicates with the truck through the cable and not through the bed of the truck. It only experiences forces that keep it on the truck through the cable and not through the bed of the truck. And then we're told that this truck is accelerating from the left to the right. So it's getting faster as it travels from the left to the right. And if the truck is accelerating and the crate is on the bed of the truck, then it's also accelerating. So an important point here is not only is the truck accelerating, but the mass is accelerating. And then we got to find this tension in this cable. Well, the key thing is here, to think about the forces that are acting on that crate. And let me draw all of them, although we could jump through just one of them to the answer. But just to be complete, we got weight acting downwards. So that's one force, and that would be mg. We've got the normal force from the bed of the truck on the crate, stopping the crate fall on the floor or the road, right? And so that's balancing the gravitational force. It's equal sized, opposite direction. And then we've got a tension force towards the right, and there's no friction force towards the right. And so what's the size of this tension force? Well, we can get that from Newton's second law, right? Newton's second law is that the sum of the forces determines the acceleration through this little equation here. Well, if we know the acceleration and we know the mass, we know what the sum of the forces must be. It must be equal to ma. And if we just think about the horizontal direction, so the acceleration is in the horizontal direction, the net force must be in the horizontal direction. Then the only force that's acting in the horizontal direction is tension. And so it must be that the tension in the string is ma. And so that would be the answer to this problem, that the tension in the string is ma. If there was friction on the bed of the truck, then the tension would be less than ma because friction would help out. So if there was friction and the cable, it would be a more complicated problem where there's both the tension force and the frictional force that would be helping the crate on the truck, accelerate with the truck. In this case, it's just the tension and not the friction. Okay, so I'm just looking back in the chat. Ashley, if you looked at force in number 4, would it be correct in saying that F1 is greater than F2? Yeah, so that's going back to the pulley problem. Yeah, that's exactly right. So if the two accelerations are the same, then a heavier mass, so M1 is heavier, would need a bigger force to accelerate it. And the lighter mass would need a smaller force to accelerate it. So, if you had an elephant and a mouse on the two sides of the arrangement, their accelerations would be the same, but the forces, the net forces on them would have to be different to give the same acceleration to the heavy elephant and the light mouse. So yeah, that's true. F1 is greater than F2. Okay, let me clear this junk here. And go on to the next problem. So now we're on the numerical answers. So I got to get my, I did at least attempt to solve the question ahead of time. So it says an athlete runs a 5. Actually, okay, there's actually a typo in what I've written, which makes it kind of a ridiculous question. In the initial sentence, it says 5,000-kilometer straight line race. That should be 5 kilometers. I'll change that. So let's take it as 5,000 meters, which is an actual race, not a 5,000-kilometer race, which would be kind of like a death race, I guess. So we're told the athlete runs the first 400 meters. We're saved here because then I did start using meters. First 4,000 meters at an average speed of 4.5 meters per second. And then the second 1,000 meters a bit faster. You get into, this happens in a race. You're getting towards the end, you got a little bit of extra strength. So you really push it. And the athlete ran that at 5.3 meters per second. So what's her total time in seconds? Okay, so this is number 6. And the total time, the way I thought of it, is the time for the first stage of her race plus the time for the second stage of the race, meaning the time that she took when she was running at 4.5 meters per second and plus the time she took when she was running at 5.3 meters per second. Now, the time for that first stage, we're not directly told the time, but we're told her speed and the distance. So we can use the relationship between speed, distance, and time, right? Speed is distance divided by time, and write down what the time is. So the time would be the distance, I'll call it D1, divided by her speed. Let me not call it V. Let me call it S. I've already got in, I spend class number 2 saying in physics, we distinguish between speed and velocity. And then as soon as I get out of class number 2, I start not distinguishing speed and velocity. So I'm really going to try hard here. Anyway, so the time for the first stage is the distance traveled divided by the speed. Look, just think whether this makes sense. The greater the distance, the more the time. That's obviously true. The greater the speed, because in the denominator, less time. That's obviously true. So it's the right way around. And then the same thing for the second stage of the trip. And so then you just got to fill in the numbers of 4,000 meters, 4.5 meters per second, 1,000 meters, 5.3 meters per second. You can see here that the units of meters over meters per second will give you the units of seconds. So the meters cancel out and they leave behind a seconds. So it's dimensionally correct. And I won't do the calculation here. 4,000 divided by 4.5 plus 1,000 divided by 5.3, I got this number of seconds, 1,078 seconds. I don't know what that is in minutes. It's pretty fast, isn't it? Because it's 60 seconds in a minute. So let's see, 600, so it's maybe 17, 18 minutes for a 5K. That sounds pretty fast. Okay, well, anyway, that was an exercise in sort of our definitions of speed and distance and how speed is related to distance traveled and time taken. Number 7. Okay, number 7 gives a graph of position versus time. So I'm not going to attempt to redraw the graph here, but I will at least sketch out the axes. So this is what we mean by a position versus time graph. So position is the dependent quantity, and here time is the independent quantity. We're watching the position versus time, position as a function of time. And we're asked to figure out the average velocity of the, for the graph. So it looks something vaguely like this and whatever. We're asked to figure out the average velocity for between the initial time, I'll call it T1, is 2 seconds. And the final time, I'll call it T2, 6 seconds. So we can look up on the graph 2 seconds, and we can look up on the graph 6 seconds, and we can read off what the position is at those 2 times. And at the time of 2 seconds, the position is 10 meters, plus 10 meters. And at 6 seconds, the position x2 is, well, it's actually at the origin at that point. And so these are the 2 time position coordinates that we need to solve this problem of what is the average velocity. So the average velocity, if you remember, is delta x, the displacement, divided by delta t, the elapsed time. So here that's like the final position minus the initial position, divided by the final time minus the initial time. It's kind of a wonky t, but it's meant to be that. And so we've got in the numerator 10 meters minus 0, plus 10 meters minus 0. In the denominator, 6 seconds minus 4, 2 seconds, so that's 4 seconds. And so this comes out to be, there should be a minus sign. Sorry, I made a mistake. Where did I make a mistake? I made a mistake right at the end. This should be a minus sign, because x2 is 0 and x1 is 10. So this is minus 10. And so that's going to give us a minus 2.5 meters per second. And so that was my answer to that one. This one is really, it's about, again, the relationship between velocity and position and time, but it's also about an important thing about being able to read these things off graphs. So it's an exercise that we did in probably in lectures 2 or 3 about reading graphs. Okay, number 8 next. Number 8 says, a plane flies 200 miles an hour in a direction that's 30 degrees west of north. Assuming that east is the positive x direction and north is the positive y direction, calculate the x component of the plane's velocity. So let me make a little sketch for this one. Here's the plane's velocity vector, and its length is 400 kilometers. No, it's miles. Sorry. Oh, got rid of everything. Start again. Velocity vector 400 miles per hour and directed at 30 degrees. So west is over here on the left, east is over here on the right, 30 degrees west of due north, vertically upwards. Now, that's a description of the velocity vector, but an alternative description, as we've seen, is components. So we can also describe that velocity vector in terms of the y component and the x component. And so we're asked to figure this component here. And so I just used a little bit of trigonometry to figure that out. So the x component, if we look at this triangle that I've constructed out of the velocity vector itself, which is the hypotenuse, and the components, the horizontal and vertical components, you can see that the velocity vector is the opposite side of this triangle. And so V sine theta, not V cosine theta, V sine theta will pick out of the velocity vector this opposite component, opposite to the angle here. And also I'm noting that, look, that tells us the length of this side of the right angle triangle. But in the question we're told that the x direction is towards the right here. The y direction is vertically upwards. So this Vx, this velocity component, is in the negative direction. So I've put that in here. Anyway, then I can stick in the 400 miles per hour, and I can stick in the angle is 30 degrees. And the sine of 30 degrees is, what is it? It's half. And so I'm going to get minus 200 miles per hour. Okay. Let me just look at the chat again. I keep forgetting to do this. From Tyler, is that supposed to say D2 over, oh yeah, that's a, thank you. There was this should be S2. Let me correct that. D2 over D2 would be ridiculous for many reasons. It would be dimensionless, so it wouldn't have a time, and it would be 1. And so it wouldn't matter, you know, how fast or slow the runner was going. That would be ridiculous. Other question, how do you know when to convert miles per hour to meters per second? In a problem, I would tell you, if I want you to convert in a problem, I would tell you to convert miles per hour, meters per second. I think what I should have done on this problem is say, give me the answer in miles per hour. So I'm going to try and make sure I'm doing that on the real test. Because, I mean, otherwise you wouldn't know. But as a default, I would, unless I tell you to convert the units in a problem like that, I wouldn't be converting the units. I hope that answers that question. There was another one. How would you want us to round the answer in number 6? Okay, so I think that's a question about the precision here. And so that's actually an interesting question. How precisely would I want you to give that answer? And I think I would give the answer to, as many digits as would take you to the decimal point here. I did put a range on it when I put in the answer, and I put from 1070 to 1080. So I put in a range as if, you didn't need that last digit, but I would always err on the side of adding extra digits. I'm not on significant figures, right? I'm not, there's nothing about having exactly the right number of significant figures. I mean, in reality, in physics, I always write down, at least one more significant figure. And so I would tend to do that. You can't lose anything by adding a significant figure. But if you didn't put in enough significant figures, then, if you wrote this as 1,000, then you wouldn't get it right. From Ashley, are the questions on the practice exam a good reflection on the difficulty of the exam? Yeah, I mean, they're meant to be, yeah. I was intended to make the practice exam and the real exam of similar difficulty. Of course, with the practice exam, you don't have a time limit of 1 hour, so that could make it harder if you spread it out a bit. For the real exam, for the practice exam, you don't have a time limit of 1 hour. So it could seem easier if you just, gradually work through it. Practice exam, you don't have, there's that anxiety, I guess, of taking an exam. The anxiety of an exam, depending on who you are, can be a good thing, right? It, gets you really working hard, or it can be a less good thing. It becomes overwhelming. But the actual content are meant to be the same level of difficulty. But they're not the same questions for sure. Number 9. Okay, so the ball is thrown vertically downwards at 9 meters per second from a 12-meter high rooftop. Calculate the ball's speed the moment it hits the ground. So here's a picture of number 9. This is the ball heading downwards. And we're told a few things here. And we're told that the initial speed of the ball, 9 meters per second. And so that's sort of telling us that we're picking, when I've written this here, this initial velocity, I picked downwards as the positive direction. You could do the calculation with downwards as a negative direction, but that's a choice. When you answer for the speed, though, you want to answer for the speed. But anyway, I picked downwards as positive. And then here's the final velocity. We don't know that. There's a couple of other things we do know. So the displacement is 12 meters. Well, that's not very clear. The displacement is 12 meters. And the acceleration of gravity, we also know that. That's 9.8 meters per second squared. And all of these quantities here are consistent with this choice that I made that downwards is the positive direction. So the initial and final velocities are downwards. So they're positive. The displacement is downwards, it's positive. The acceleration of gravity is downwards. And so everything was downwards there. Now we want to find out the final speed, and so that's solved, this problem is solved by thinking about our equations of motion. And here's the one that will work for us. I'm applying it to the vertical motion, so that's why I'm going to hang little y's on here. Maybe should have done that to begin with. I'm thinking about vertical motion here. And if you look at this, this equation of motion here, well, we know the initial velocity, we know the acceleration of gravity, we know the displacement. So everything on the right is known. We just need to plug in the initial speed, the acceleration, the displacement, and we'll come up with the final velocity. This is an equation for the velocity squared, so I've got to take the square root to find the final velocity. The initial velocity is 9 meters per second. So stick that in. And then we've got, let's see, 2 times acceleration of gravity, 9.8, times displacement, 12 meters. I'm not writing all the units. And if you do that calculation, the number I got, let me see if I can find it here. I got 17.8. 17.8 meters per second. And so that's the downward velocity. Let me look in the, could you specify the difference between velocity and speed? Yeah, so that's been answered by Sarah, and that's completely correct. Velocity is a vector. It has a direction to it. So if I say I am walking at 3 miles an hour north, I'm describing my velocity vector. Speed, on the other hand, if I just say I was walking at 3 miles an hour, that's just telling you this, you know, this magnitude of my motion. It's not telling you the direction, so that's speed. Actually, Sarah wrote it more clearly than I said it. Okay, number 10, I think we're on now. And this one's about a beer glass falling off a table. Let me clear this slide. Okay, so here's the bar, here's the floor, and we've got the beer glass here, and it's going to slide off the table, fall to the ground. Sad event. And we're told that the glass was initially sliding in the horizontal direction. I'm going to write down the numbers we're told. And this is, what was this? This is number 10, I think. V naught x of the glass is 0.8 meters per second. So we're told that. We're not directly told it, but also we can infer it, that it slides across the horizontal table. The initial velocity in the y direction, that's actually 0. So that's important. And then we're told that the distance fallen, that's the vertical distance fallen between the bar and the floor, that is 1.3 meters. So I'm going to call that y minus y naught. And then, of course, we know that the acceleration of gravity is 9.8 meters per second squared. So that's the information that we know in this problem. Now, when I've written down these numbers, this is the positive x direction from left to right. And this is the positive y direction from the bar top to the floor. And, you know, we could have chosen a different convention for that, but I just chose that. And we want to know the distance from the edge of the bar to where the glass hits the ground. Maybe we want to try and catch it. And then we would want to know this distance. Anyway, so to solve this, I did this in 2 steps. The first step, I considered the vertical motion. And then the second step, I considered the horizontal motion. And the first step of the vertical motion, I used to find the time that it took to get to the floor. And once I knew the time that it took to get to the floor, then I went on to look at the horizontal, this is meant to say, the horizontal motion, and find out this distance that it traveled horizontally. So it's 2 stages in that respect. Now, for the vertical motion, I considered the following equation of motion, that the displacement for a trip is equal to v naught yt plus 1/2 ayt squared. This equation here. So it's just that one of those 3 equations of motion applied to the vertical direction. Now, we know that displacement is 1.3 meters in the vertical direction. We know that there's no initial velocity in the vertical direction. We know the acceleration in the vertical direction, acceleration of gravity. So the only thing I don't know in this equation is time, and so I can solve for time. And time, if you rearrange the equation, comes out to be twice the displacement divided by the acceleration of gravity, and then the square root of that. And I won't plug in, I'm running out of room, so I won't plug in the numbers, but we're going to plug in, obviously, the 1.3 meters displacement and 9.8 meters per second squared acceleration. And then we're going to take the square root of that. And I think my writing's really bad on this bit, but it looks like I got 0.515 seconds, so half a second to hit the ground. Okay, so now I know the time that it took to reach the ground. Now I can really think about the horizontal motion. So here I do want the displacement horizontally, and the same equation of motion would actually give you that. The initial velocity times the time for the fall plus 1/2 axt squared, but there's no acceleration during the fall in the horizontal direction. And so this equation simply says that the horizontal distance traveled is just the, oh, what's going on? I've pressed something on the pen here. This is ridiculous. I don't know who invented the drawing pad, but it's not been a good experience for me. So this horizontal displacement is going to be v naught, just v naught x times time. And look, we know the initial velocity is 0.8 meters per second, and we know the time elapsed is half a second. And if you multiply these two, you get about 0.67 seconds. And so that was my answer to number 10. And so that was a nice example of projectile motion, or maybe, depending on your viewpoint, a not nice example of projectile motion, where you have to think about, well, we understand projectile motion as this kind of superposition of horizontal motion and vertical motion. That's how we understand these, complicated parabolic trajectories of projectiles. Okay, number 11 is the next one. And number 11 says we got a block of mass 1.6 kilograms. It's accelerated vertically upwards by a cable. And the cable will break at 40 newtons tension. And so what's the maximum acceleration? So it's important here, we're thinking about the situation where the tension is 40 newtons. We're at that maximum. And we're thinking about this 1.6 kilogram block that is experiencing that upwards tension and the downwards force of gravity. So the force of gravity, or the weight, is mg. And so since I know the mass, I can multiply 1.6 times 9.8, and that came out to be 15.7 newtons. So we're thinking about this block. It's got an upwards force on it, 40 newtons, and a downwards force on it of 15.7 newtons. So we want to figure out the acceleration. Well, that's an example of Newton's second law, right? The sum of the forces equals mass times acceleration. So we just need to change that around to calculate from the sum of the forces and the mass, the acceleration. The sum of the forces in this case is there's tension up and there's weight downwards. Divide that by the mass and plug in the numbers. So I won't write that, I'm running out of space. 40 newtons minus 15.7 newtons. That would be 24.3 newtons. 24.3 newtons divided by 1.6 kilograms. I got for the answer of that looks like 15.1 meters per second squared. And so that was my answer to that one. That's an example of the Newton's second law. Finally, 12. Okay, so 12 is the problem that you'll submit by writing out fully the solution. And it says, consider a 1.5 kilogram block sliding down an incline at 25 degrees. We're told the coefficient of kinetic friction between the block and the incline is 0.14. We've got to calculate the normal force on the block, the friction force on the block, and the acceleration of the block. So this is a problem that I always start by drawing a diagram. So here's the incline, 25 degrees. And then we've got this block.
Is it possible to maybe move the screen up or draw the problem a little bit? It's getting cut off.
Oh, is that right? Yeah,
yes.
That's fine. Okay, yeah, I can. Yeah. I'll just clear this and do it again.
Thank you.
Okay, so let me redraw. Here's the incline, and here's the block. And we know the mass of the block, don't we? 1.5 kilograms. I'll just write 1.5 here. And then what we're going to do is the usual thing where we sketch out the forces. And that will lead us to the calculation of the forces. And I think it's really important to sketch them out before you start calculating them, because somehow the picture just leads you to the calculation so much more straightforwardly. Okay, so the forces are, we've got weight. That's acting straight downwards. And the weight is the mass times the acceleration of gravity. And the weight is, I've got to find my solution to this problem. I worked it out. 1.5 times 9.8. Yeah, that's 14.7. So that's the weight of the object. Then in this problem, there are two other forces. there's a normal force, and there's a frictional force. And the rule for the normal force, right, is that it is perpendicular to the surface, and the frictional force is parallel to the surface. So that's how I've drawn these two forces. But right now, I don't know the values of these two forces. And you know, a large part of this question is to solve for the value of these two forces. So let's start thinking about that. Now, to solve for the value of these two forces, what I'm going to first have to recognize is that weight, that force of gravity, we're going to want to resolve it into two components. One that acts parallel and one that acts perpendicular to the incline. This one that is parallel is the weight, 14.7 newtons, times the sine of the angle of the incline. It's because this is also 15 degrees. And the one that is perpendicular, that's this guy here, is the weight times the cosine of that angle of 15 degrees. So that resolution of the vertical weight, the vertical force of gravity into these two parts, parallel and perpendicular to the incline, is a key thing that we do on these incline problems. We always resolve weight into these two components. So the reason, here are the reasons we do that. So the normal force, which is stopping the mass, you know, crash through the incline, precisely balances that component of gravity into the incline, precisely counteracts W cosine theta. So it has the same magnitude, opposite direction. So that's really what determines the strength of the normal force in the incline. And then the friction force on the incline, that's the rule for the frictional force, is in proportion to the normal force. And the coefficient of friction is that proportionality constant. And so this is my picture here of the problem, of the forces involved in the problem, and how they act together to firstly support the block on the incline, and secondly, to accelerate the block down the incline if this component of weight overcomes this frictional force. So now we can, at that point, we can go on and figure out the sizes of these things. Let's do that over here. The normal force is equal to the weight times the cosine of 15 degrees. And so the weight is 14.7 newtons. We multiply it by the cosine of 15 degrees, and I got 14.7 newtons. So that's the calculation of the normal force. That's one of the two things we were being asked. Friction force. Well, friction force is the coefficient of friction times the normal force that we now know. And I didn't write it down here. Let me just note it. We do know the coefficient of kinetic friction. It was 0.14. And so we just got to multiply the 14.7 by 0.14, the coefficient of friction. That comes out to be 1.9 newtons. So that's straightforward now. We got it from the picture. And then finally, we also want the acceleration of the block down the incline. Well, the acceleration down the incline is due to the forces that act down the incline. I'll put a little x in here. I call this the x direction along the incline, divided by the masses. So that's Newton's second law. And in this case, there are two forces that act down the incline. There's this frictional force, which is 1.9 newtons. That's acting upwards. And then there's this component of gravity that's acting down the incline. So that's 14.7 newtons times the sine of 15 degrees. And I also worked that out. That was 6.2 newtons. And this one up here was the 14.7. Anyway, so downwards, down the incline, call that the positive direction, we've got a 6.2 Newton component of gravity. Up the incline, opposing the motion, we got a 1.9 Newton friction force. And if we combine those, we're going to get, let's see, roughly 4.3 newtons. And we're going to divide that by the mass, which is 1.5 kilograms. And if we do that calculation, I got 2.9 meters per second squared. And so that was my 3 answers, 1, 2, 3, for this question. And I would say I showed all the working out in the sense that I drew the diagram, I drew all the forces on the diagram and the components of weight on the diagram. I wrote the equations for the components of weight. I wrote the equations for the normal force, for the frictional force. I then carried out the calculation of the normal force, the frictional force. I wrote the equation for the acceleration, Newton's second law, and I filled in the forces and carried out that calculation. Okay, so I'm done. I did it in 1 hour. Now, you know, I should be able to do it. I'm very old, and I've been doing this for a very long time, so I should be able to do it way quicker than 1 hour, but I was talking at the same time, and I was writing. The other thing that slowed me down was that I was using the drawing pad, which multiplied the time it took me by, say, 10 to finish it. But anyway, that's the problems on the practice exam. What was your answer for number 10? I gotta go back. I think it was 0.67 meters. I remember this is the beer glass one. So if I'm remembering it correctly. Yeah, I can't actually read my writing here. Maybe, do you want me to check that one? I can quickly do it on my calculator here. Because maybe I gave the wrong number. So we're told that it falls from 1.3 meters. So the time is the square root of 2 times the distance divided by the acceleration of gravity. So that was 0.515 seconds. And then we got to multiply that by the speed, 0.8. And so that's 0.41 seconds. So I think did I write 0.67 seconds, 0.67 meters per second on the exam? I can't remember what I wrote. Yeah, so I did. So it should be 0.41. Sorry about that.
For number 9, once I submitted the quiz on Canvas, I put that we had answered like 17.8, but it's saying that the correct answer is between 310 and 320.
Yeah, I think that's my mistake, that it should be the square root of that, so that you had the correct answer. And I think I wonder if I've fixed that now. I'm afraid this is me learning how to do Canvas exam for the first time. But you know, the number that you had, 17.8, is exactly the right answer.
Okay, and then just to make sure, whenever we do submit our answers for the numerical problems, we don't need to put the units, correct?
You don't need to put the units. And I think what I need to do is to make it clearer what units you're answering in. I.e., there was one about where it's miles per hour. Well, should I be converting that to meters per second? And I didn't expect you to, but it probably wasn't clear. So I'm going to look back through the exam for tomorrow and try and tidy that up. Any other questions on all that?
I was wondering if you could go over one of the problems that was in the book, or the homework problems.
Yeah. Can you tell me which homework and which problem?
Let me find the. I think it was question 10 on the homework 4. I don't know what chapter that's from, but it's question 10 on WebAssign, question 58 in the textbook.
Okay, homework 4. I just got to find it here. And number 10. Is this the, this is the one with the various drawings involving springs?
Yeah.
And pulleys and, yeah, okay. So.
I just didn't understand why the first one, the one with the, like the one on the top left, how that one was half of the pulley one. If they both had like 2 objects hanging from the same string.
They do have 2 objects, yes. So that's a very good question. So maybe if they had drawn that, like, look at C. So there's a single string that's connecting the 2 masses, right?
Yeah.
And so in C, you mind if I better quickly read the question before I start saying things randomly. The system shown below in equilibrium, the spring scales are calibrated in newtons. What do they read? And we're told the mass. Yeah, okay, so in C, right, that string, the tension in that string is 50.3 newtons. Are you okay with that?
Mm-hmm.
So A is kind of like, well, we stretched out the pulley in C to 2 pulleys. So if I just had 2 pulleys upstairs, would you agree in A, would you agree that that's 50.3 newtons?
Wait.
Let me
How'd you
draw
get
it.
the 50.3 newtons? I'm sorry.
Yeah, so I'm trying to explain A by thinking about C.
Okay.
Because C is, part of C at least, is something that we've looked at in detail. So kind of here's 10C, right? And these weights of 5 kilograms roughly, and the tension is like 50 newtons. So you're okay. Are you okay with this being 50 newtons and this being 50 newtons?
Yeah.
Because, think about it. The force of gravity is pulling down by 50 newtons, isn't it, over here? So it must be 50 newtons tension here. And the force of gravity is pulling down by 50 newtons here. Okay, so now let's just change 10C a little bit. And I'm going to put in 2 pulleys, but just still that 1 piece of string, right? It goes over the 2 pulleys. And so you probably would agree then that this is also still 50 newtons and 50 newtons, right?
Yeah.
Because again, really 1 pulley, 2 pulley, it's really this single piece of string. Mm-hmm. So then the only difference that's made from this one in 10A is that we put a spring in here. Well, the spring, that spring or that force or the scales just measures the tension in that particular cable or wire. So that 450 Newton tension is just being transmitted through this string. So this is also 50 Newtons. If I had hung the two masses like this, then this would be 100 Newtons and this would be 50 Newtons. So then, you know, this string has twice the tension as this string because it's supporting both masses rather than one. But this string here is really just supporting one mass on either side here, just like this picture. It's just transmitting the, think of the string as kind of transmitting the tension from one side to the other side. And that transmitted tension is still 50 Newtons.
Oh, okay, gotcha. Can you also do part D, the one with the incline?
Yeah, the one with the incline, is it frictionless? Yeah, must be frictionless. So let's remove a bit of this. So here's the incline, and here's the string that's supporting the mass on the incline, and there's no friction. And this one is actually, you know, we did a lot of things in class. You might not remember it, but we sort of did this problem in class. In this case, right, there's obviously gravity is pulling downwards.
Mm-hmm.
There's the fact that we can resolve gravity into these two components, right? mg sine theta and mg cosine theta. So gravity has a horizontal and a parallel and a perpendicular component. And then it's not so relevant here. There's a normal force over here. So the tension in the string here must be balancing, counteracting this fraction of gravity. So its magnitude is mg sine theta. And so the tension that they calculate, you probably have different numbers from me, but I would put in the angle of the incline, you know, whatever it is, put in the mass, whatever it is, and that should give you the tension in that particular string. Does that make sense?
Yeah. Okay, gotcha. Thank you.
Any other questions?
Oh, I have one more.
Mm-hmm.
So you know how whenever you choose, like doing the problems with velocity, how it could be like negative or positive depending on what direction you determine to be negative and positive?
Yes.
If we were to do that, will the test accept both the negative and the positive answer for velocity as long as the value is the same?
So what I have to do in the test is that I would have, that's why you'll notice in some of the test questions I said, you know, choose the positive direction as this. So if I say that, you'd have to be consistent with that, and then the sign would matter. Or I might say calculate the speed, in which you just put in the size.